Hi everyone, my name is Rin Bowman and today I'm presenting Lab 3, Black Hole in Orbits. The goal of this lab was to use computational modeling to study orbital motion by applying the universal law of gravitation and Newton's second law. Using GlowScript, we simulated how objects move under gravitational forces and visualized their motion over time. The main purpose of this lab was to understand how gravity affects motion in space. Instead of solving equations once, we used computational modeling to repeatedly calculate forces, velocity, and position over small time steps. This allowed us to simulate how objects move under gravitational forces and observe orbital behavior. In part 1 of the lab, we modeled a star orbiting a black hole. The black hole was placed at the origin of the coordinate system, and the star was given at an initial position and velocity. Using the universal law of gravitation, we calculated the gravitational force between the star and the black hole, which always pointed toward the black hole since gravity is an attractive force. After calculating the gravitational force, we used the momentum principle, which is Newton's second law, to update the star's motion. The program repeatedly calculated the gravitational force, updated the velocity, and then updated the position. By repeating these steps many times, the simulation produced the orbit of the star around the black hole. Another important part of this section was analyzing how the star's momentum changed over time. We calculated the change in momentum to determine the net force acting on the star. We also separated the force into components parallel and perpendicular to the momentum. This helps show how gravity affects both the speed and direction of the star's motion, which is what keeps it in orbit. Using the calculated force and the distance between the star and the black hole, we were able to estimate the mass of the black hole. This part of the lab demonstrated how astronomers can determine the properties of objects that cannot be observed directly by studying the motion of nearby objects like stars. In part 2, the system became more complex. Instead of just two objects, we modeled a planet, a moon, and spacecraft. The moon orbited the planet while the spacecraft experienced gravitational forces from both the planet and the moon. This meant that we had to calculate multiple gravitational forces and add them together to find the net force acting on each object. And so this was the system and the surroundings. The system was the star, and the surrounding for part 1 was the black hole. And then for part 2, the system was the spaceship, and the surroundings were the moon and the planet. And so this was the code that was used to calculate this. This was the results. As the star got closer to the black hole, the arrows grew in size accordingly. And something similar was that the results generally remained consistent with Newton's law of universal gravitation. But however, slight variances of the calculated model values for mass could be observed due to rounding and minor differences. And for part 2, all given values of gravitational constant, planet mass, moon mass, spaceship mass, and change in T initial, and T max are specified, which are below in the findings. And so the edited code were as follows: the calculations for the net force on the moon, calculations for the net force on the spaceship, formulas for the position update and velocity update. So some sources of error could possibly be just like errors in calculations. There might be an error in trial and error method for the initial velocity in part 2, and then a possible error in maybe code. And then these were the results. So something that was similar is, as predicted, Newton's laws were characterized in the simulation, and the difference was that the orbit was not identical and did not appear as a figure 8 orbit. So the net force on the star equals the rate of change of its momentum, so they point in the same direction and have the same vector components. Decomposing along the motion, the parallel component changes the speed, so speeding up or slowing down, while the perpendicular component changes the direction of the velocity, so the curves in the path. Thus, the observed change in momentum is just the vector sum of these parallel and perpendicular effects of the net force. The model we would need to include the gravitational forces between all 4 objects, the black hole, star, planet, and moon, because each object's motion depends on the gravitational pull from every other body in the system. The strongest or dominant interaction would occur between the black hole and the star, since the black hole has the greatest mass and exerts the largest gravitational influence. The planet and moon would mainly interact with each other, creating a smaller scale orbital system within the larger one. However, weaker gravitational effects from the black hole and star would still influence their motion over time. So including all interactions would be necessary for an accurate and realistic simulation of the system's behavior. Overall, this lab demonstrated how the universal law of gravitation and Newton's second law can be used to model orbital motion. By using computational modeling, we were able to simulate systems that would be difficult to solve by hand. The simulations help visualize how gravity influences motion in space and showed how physics can be applied to real astronomical systems. Thank you for watching.